This cannonball is both moving forward and falling at the exact same time. That sounds impossible, but once you realize that projectile motion is actually just two separate motions happening simultaneously, these problems become much easier. Today, we'll go over projectile motion and solve some problems step by step. If we take a closer look at our cannonball, we can see from the vector that I've drawn the direction of motion that the cannonball is going in. We can break that vector into its horizontal and its vertical component. And we can analyze each of these components separately. What this means is that these two components are completely individual of each other. For example, gravity is going to act on this cannonball at all points during the cannonball's motion. But gravity is only going to act in the vertical direction. So we only need to worry about this blue arrow whenever we're worried about gravity. Let's first ask ourselves about the ball's acceleration. We know from the previous video that anything in space has the force of gravity acting on it. That's our gravitational constant, g. On Earth, this gives any object a constant acceleration of negative 9.8 meters per second squared, if we choose up to be the positive direction. This describes the motion in the vertical direction for the ball, explaining why it is technically falling. I've chosen a sub y to describe the acceleration in the y direction. This ball is also moving forward, as you can see in the diagram from this red arrow, due to the momentum it gained from the cannon. However, the cannon already acted on the ball, so currently there's no force causing the ball to actually accelerate in the horizontal direction because the cannon acted on the ball in the past. That means that the acceleration in the positive or the x direction is actually 0 meters per second squared. The ball still has an initial velocity in the x direction, but it doesn't have an acceleration in the x direction. So we know that these arrows, the blue and the red one, represent velocity in the x and y direction. If we have a velocity vector, that's the black one, with some magnitude v, and we know the angle to the horizontal theta, then through trigonometry, we know that the component in the x direction, so v sub x, is equal to v cosine theta. And also through trigonometry, let's move this over a little, v sub y is equal to v sine theta. And we can solve the kinematic equations in the x and y directions. Let's give v and theta some values and see what happens. So we'll say that v is equal to, we'll say 20 meters per second. So the velocity of the ball right when it leaves the cannon is 20 meters per second. That's the overall velocity, containing both horizontal and vertical components. And let's say it's launched at an angle of 30 degrees to the horizontal. We then know that the velocity in the x direction is equal to 20 times cosine of 30, which if you plug it into the calculator is equal to about 17.3 meters per second. And then the velocity in the y direction is equal to 20 sine of 30. Give ourselves a little more space again. Which is equal to roughly 10 meters per second. So what this tells us is the initial velocity in the x and the y direction. A common question that may be asked is how long until the projectile lands, in which case we would want to know time. So now we have velocity in the x and y direction, we have an acceleration in the x and y direction, and we want to know time. So we know the velocity in the y direction is 10 meters per second, which we saw from here. And we know the acceleration in the y direction, which is just negative 9.8 meters per second squared. But we only have two variables here, and for any of the kinematic equations, we need three known variables. So what else do we know about this problem? Well, if we draw it out, this is the path that the ball follows. Here's the ground. It starts here at this point, and it ends here at this point. We say there could be some delta x, but that doesn't help us because we don't know that. What about delta y? Well, it starts here at y equals 0, and when it hits the ground over here, we know that y also equals 0. And so we know that delta y, or the change in y, is equal to 0 meters. Now we have 3 variables with time as the unknown, and we can set up our kinematic equation. That's going to be delta y equals the initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. So we have everything we need to solve this problem for time. I'm going to plug our variables in now. We have 0 equals 10 times time minus 1/2 9.8 t squared. The minus comes from the negative 9.8. We could use the quadratic equation to solve for this, but we could also just use a little algebra trick. We can factor t out of both of these, and we get that 0 equals t times 10 minus 1/2 9.8 t. This tells us that either this t equals 0 or the inside here equals 0, because we have the 0 on the left-hand side. So we know that t is equal to 0 and then some other value. So we have 0 equals 10 minus 1/2 9.8 t. We can rearrange this by adding the 1/2 9.8 to both sides. We have 1/2 9.8 t equals 10. Multiply both sides by 2. And we have 9.8 t equals 20. And then we divide both sides by 9.8. And we get that t is equal to about 2.04 seconds. And these are our 2 values of t. And this makes sense if we look at the path again, because there's 2 instances at the very beginning when time equals 0, and at the very end when time is, we found to be 2.04 seconds, where the change in y, or the location of y, is 0 meters. Now that we know the time, which I've written on the left here, a problem like this would likely ask you to find the change in x. We're dealing with the change in x now, so I'm going to erase these variables that deal with y, and instead write down the x variables. We have Vx equals 17.3 meters per second. And remember, we found that earlier with our trigonometry. We have delta x as our unknown, and we have acceleration of x is equal to 0, because there's nothing acting on the ball throughout its arc. We can rearrange this equation to be in terms of x instead. Delta x, v sub x, and a sub x. That's a v. There we are. Notice that acceleration due to x is 0 meters per second, which means that this term is 0, and so it cancels completely. We can erase it. And we're left with delta x equals velocity due to x times time, both of which we have. So delta x equals velocity in the x direction is 17.3, and time we found to be 2.04 seconds. And this equals about 35.3 meters. And let's say the problem now that we want to know is the height that the ball reaches. Height deals with velocity in the y direction, so let's solve that. Vy is 25 sine of 45, which if you plug it into the calculator is roughly 17.7 meters per second. So now we have Vy we have acceleration in the y direction, and we know that we want height, which we can say is our delta y. We know it starts at 0 and it's going to reach some height. So we need one more variable to make this problem work. If we look at the arc again, same thing happening. Right here at the point, it changes direction. If you remember from the very first video in this series, anytime that something changes direction, the velocity is 0. And so we know that the final velocity at the peak of the arc is 0 meters per second. Now we have 3 variables and 1 unknown variable, and we can use one of the kinematic equations. The one that uses all of these and is missing time, notice we don't have time, is final velocity squared is equal to initial velocity squared plus 2a delta y. So let's solve this equation for delta y symbolically. We have final velocity squared equals initial velocity plus 2a delta y. I'm going to subtract out the initial velocity squared on both sides, leaving us with final velocity squared minus initial velocity squared equals 2a delta y. And then I'm just going to divide both sides by 2a. So our answer is final velocity squared minus initial velocity squared over 2a equals delta y. Now we can plug in our variables. Final velocity is 0. Initial velocity is 17.7 squared divided by 2 times negative 9.8. And I'm just going to plug this into the calculator, but it's a good point to check here our sign convention. We have a negative 9.8, and we have this negative 17.7 squared. A negative divided by a negative is a positive, and so we know we'll end up with a positive value, which makes sense because we're going to have a maximum height, which if we're still defining up to be the positive direction, should be a positive number. But if we plug this into the calculator, we get an answer of roughly 16 meters as the maximum height. Here are the key takeaways for how to solve any projectile motion problem. First, you list any and all accelerations. Normally in projectile motion, this is just gravity, and so vertically the projectile behaves exactly like a normal free fall problem. After that, we break all vectors, normally the velocity vectors, into 2 components, the horizontal and vertical component. From there, we solve vertical motion and horizontal motion separately and combine the results to answer the question. We do so by listing the variables, picking the kinematic equation, and solving them. If you remember to do these things, to split your velocity into components, treat the horizontal and vertical motions independently, and let gravity only affect the vertical direction, you'll have what you need to solve pretty much any introductory projectile motion problem. And in the next lesson, we're going to go over even harder projectile motion problems. We're going to go over launches from different heights and problems where you need to hit a specific target, things like that. If there's a physics topic you'd like to cover in a future video, or if you have a particular question you'd like answered, let me know in the comments below. I read every suggestion you guys give, and your ideas help shape what I teach next.